Okay, welcome back, everybody. So for those of you who've been following the videos online, we were not able to tape the last lecture, so I'm just going to summarize what we did in the last lecture, since most of you were here, but for those who are watching online, you might wonder what we did last time. So what did we do? 2 lectures ago, we introduced this notion of continuity. What does it mean for a function to be continuous? And we talked about the metric definition of continuity. We also talked about the sequence definition of continuity. And last time we spent a lot of time talking about a third definition of continuity in terms of open sets. So just to remind everybody, the metric definition of continuity says basically that close enough points get mapped to close points. That is, if I give you an epsilon, you can find me a delta such that anytime 2 points start within delta of each other, they map to within epsilon of each other. Okay? For a particular, at each point P, you can find such a delta given any epsilon. Okay? And the function, say the function is continuous everywhere, means at every P you can find such a delta. Okay, that's the metric definition. The second definition, or the second equivalent condition, is that the function preserves limits of sequences. So if you have a continuous function, that means that the limit of the image of a convergent sequence is still convergent, and it converges to the limit. The f of the limit of the sequence. Okay. The third definition is completely a topological definition, and it just says that the inverse images of open sets are open. And of course, it's very closely related to the fact that inverse images of closed sets are closed. Okay, so this is what we discussed last time. We proved the third and fourth definition. Some of the consequences we saw of the open set characterization, they're very easy to see from that definition, is that the inverse image of, is that the composition of continuous functions is continuous. Why? Well, if you have a map from space X to Y and Y to Z, and these are both continuous, then you know the inverse image of an open set going from here to here is open, and the inverse image of this set is also open because this one was open. And so this inverse image of the entire composition, inverse image of an open set, is open. Very easy to see. The image of a compact set is compact. You've got a compact set here and another space here, and you're mapping it in. Well, let's take an open cover of the image here. The pre-images form an open cover here. Therefore, there's a finite subcover using only those sets. Therefore, their forward images also cover this set, and they're finite. Okay, so very, very nice. And one very, very quick consequence of that is that a continuous real-valued function on a compact set must achieve its minimum and maximum. Why is that? Well, if it's real-valued, it's getting mapped into the real numbers. The image of a compact set is compact, and in the real numbers, that's the same as being something and something. Closed and bounded. Very good. And if it's closed, then there is a point that's achieved that achieves a maximum and minimum, and it has a pre-image, and those are the points that achieve the maximum and minimum. Okay? Okay, very, very nice facts about continuous functions, and easy to see from that last definition. So what I want to talk about today is uniform continuity, which we defined last time, but I will remind you what it is. It's actually related to the concept of continuity. So the definition of uniform continuity is, let's call a function from a metric space X to a metric space Y uniformly continuous if some condition holds. So we'll say it's uniformly continuous on X if for all epsilon bigger than 0, there exists a delta bigger than 0 such that for all x, and the important thing is that not only is this true for all x, but it's also true for all p, any point p you want in x, that if the distance between x and p is less than delta, that implies the distance between what and what is less than epsilon. Yeah, f of x and f of p. So this looks a lot like the definition of continuity, except that we're saying that the same delta works for every p. You're given epsilon, the same delta works for all p in x. Okay? That's what it means to be uniformly continuous on x. Okay? Now, for the definition of continuity, remember, p is specified before you start this definition, because we were talking about being continuous at a point. And then when you say it's continuous everywhere, you mean for each point, for every epsilon, there's a delta. Whereas now we're saying, for every epsilon, there's a delta that works for each point. Okay? That's what it means to be uniform, right? It's like, you know, if we're all wearing the same uniform, we're wearing the same thing, right? So we have the same, I saw somebody roll their eyes, the same delta, that we're all wearing the same delta, okay? That's what we're saying. Okay, great. So, the picture I drew last time suggested an example that was clearly not uniformly continuous. So, for instance, you might have a function like so, and it might be, of course, this is a function that's only defined on this portion of the real line. Okay? And if I want to see if it's uniformly continuous, well, it's clearly not. Why is it not uniformly continuous? You give me a point, let's say here, P, and let's say take another point, Q. Well, here's f of Q, here's f of P. Now, if I ask, if I specify an open interval around P, an epsilon ball, then clearly, well, the delta ball that will land in this region is actually quite large. Here's a delta ball that will land in this region. So if I pick anything in this region here around P, I will land in an epsilon ball around f of P. Yes? But notice, what does it take to land in an epsilon ball around f of Q? The same epsilon ball. Well, notice that it takes a much, much smaller delta ball to land in an epsilon ball around Q. Okay? Okay, now that by itself, by checking 2 points, seeing that this delta was different than that delta, doesn't make this necessarily not uniformly continuous, right? Because you might say, oh, okay, well, look, this delta works for P as well. It's smaller, yeah? But what's the difficulty? Will this delta work for all points? No, which ones are you going to worry about? To the right of Q, this delta actually will no longer work, okay? Because this function's doing something crazy, okay? And why is it allowed to get away and do something crazy? Well, it's because the domain of this function was not, in this case, it's not compact or closed, right? I mean, this endpoint, right? If I demanded that this function end here and be defined here, this thing couldn't have gone off to infinity and still be continuous, right? So we see in a very essential way the fact that what uniform continuity is demanding of us. It's demanding the same delta work for every epsilon. Okay, so what's the big deal here? Let me show you some facts about some things we can say about functions that are when functions are uniformly continuous. So here's our first theorem, one of the most important theorems about continuity, and that is if you have a continuous function and on a compact set, then in fact f is uniformly continuous on X. So what it's saying is this example, it's sort of pointing out how you could, what sort of, where the problem is in this example. It's bringing up the fact that, if this domain had been compact, I would have been in good shape. For instance, if this domain had stopped right before it got to the asymptote, then I'd still be okay, wouldn't I? Why? If I'd stopped this domain right here, what delta would work for every point? The delta that worked at this end point, right? That would work everywhere to the left. So this sort of gives a hint as to what's going on with this theorem. Very, very important theorem. Now, why is this such an important theorem? Why do we care about uniform continuity? Well, uniform continuity basically says that, if the same delta works for every epsilon. It just means that, look, for any target distance you name, I can tell you how close you have to be to land within epsilon. It doesn't matter where I'm at. Okay? And this theorem is saying, guess what? I have uniform continuity whenever I have continuity on a compact set. Okay, so let's prove this fact. Let's prove this fact. How could I prove this fact? Let's see if we can develop an intuition for why it's true. So, how is compactness going to help me here? Any ideas? Let's draw another picture here. And let's imagine that we have a compact set. Although this, I want you to realize, X didn't have to be just a subset of the real line. It could be a subset of any metric space, right? It could be two-dimensional, three-dimensional, infinite dimensional, doesn't matter. But let's just look at a picture like this. Okay, so here's a compact set in the real line, and I have a function that's defined on it that's continuous. Help. What delta is going to work for every epsilon? You give me an epsilon ball. What delta is going to work for every epsilon? Okay, maybe that's not around a point that's, so here. Let's look at some sample points. Here's a point, and here's its image. Here's a delta ball around it. Okay. Here's a point, and here's its image. Lands in here. There's a delta ball, an epsilon ball around it. So let's see. This delta ball is kind of tiny. This delta ball is kind of big. And, I'll go over a few other places. I could find some delta balls that would keep things within epsilon as well, right? Here, maybe this one works. Now, lots of different deltas. What delta is going to work for every epsilon? For a given epsilon? For every point. The smallest one. Is there a smallest one? Not necessarily. I mean, there wasn't a smallest here. These got smaller and smaller and smaller and smaller as you went to the right. Those the requisite delta balls.
So the function achieves both its maximum and its minimum.
This function, okay, I agree.
So
This function's continuous. Is that going to be helpful to us? It achieves its maximum minimum. I'm actually interested in how big these delta balls are. How do I know these are not going to get just smaller and smaller and smaller and smaller somewhere, Willie? The point at which the slope is greatest. Yeah, okay. Your intuition is good there.
Can you make a continuous function that maps each point to the distance? Oh, like somehow make a function that maps the points to the distance because the distance is always in the real line. And then if you had a continuous function, then you could know that those values of the distances, those have a minimum and a maximum.
Okay, hold that thought. Let me just address Willie's thought. So Willie, you're noticing that if this function had a derivative, which we haven't defined yet, and which this function may not necessarily, since we only required it be continuous, but if you could talk about slopes and stuff, it certainly would make sense that the slope, where the slope is the biggest, perhaps, is where the delta would be the smallest. And this thing you're claiming maybe has you just go to the place where the slope is the biggest, if there is such a place. And there isn't one here, but there happens to be one here on the compact set. Okay, that's certainly a very good intuition. It shouldn't surprise us because, in fact, this is saying close, close, right? This is run, that's rise. Rise over run, if we could define it, would certainly be related to this concept. But unfortunately, f is just continuous, and we don't know anything about derivatives yet. Okay? But good intuition. Yes, Jenny.
I don't feel like there has to be maximum slope because if you look at like your cubed root of x that and look at that on the interval from 1 to -1 that has an infinite slope.
The cube root of x. Oh, yeah. Although that that is not right. That's right. I see what you're saying. Yes. So in fact, yeah. So the cube root of x. So your picture was something like this, right? Yeah. And so even here, the idea of an infinite slope might be the idea that there is a maximum slope is a problematic one, right? Okay. But it is a good intuition that somehow this is the slope is related to this this ratio. Okay. But yes, there are problems with this idea. Okay, but we're not even going to talk about slopes for another lecture or so. Okay. Okay, so let's come back to, so what's the other idea? Well, let's see, delta balls. Would you agree there's a delta ball around every point?
So let's make a function that maps each point to the size of the delta ball needed for a given epsilon.
Ooh, interesting. Make a function that maps each point to the delta ball around it. That's kind of your idea. And then hopefully that's continuous. Yeah, it's not such an easy direction to go, but again, the intuition is helpful. So you're going to see ingredients of all these ideas coming up real soon here. But let me just point out there are many, many ways to prove this theorem, and the book does one way, and I'm going to do another. Okay, but the book's argument goes something like this, and you'll begin to see the idea here. Every point has a delta ball associated with it, yes? Yes? Those delta balls form a cover, an open cover of this set, which is compact. Therefore, there is a finite subcover. Okay, and so then what? If you have the delta balls that cover, does that guarantee anything about? No. So there you have to be a little careful, and you have to massage things a little bit. And the book goes through a bunch of basically some metric arguments where you start with balls as bigger than you need, and take smaller things where you go for delta balls that relate to epsilon over 2, et cetera, et cetera. But the book sort of does a, let's see, a different argument, but you should look at it. Let me give you an argument that might be easier to digest, I think. I like it better. It also appeals to a famous lemma, which we'll prove. It starts off exactly the same way, though. So let's suppose we're given an epsilon bigger than 0. And our goal, of course, is to find a delta. And this delta better work for all p. For all points p. Okay? Okay. So as we noted, each point in this interval, x, has a delta ball. It might depend on x, so I'll call it a delta x ball that satisfies the condition. What condition? Such that if I look at the distance from any other point y to x and demand that it's less than delta, then in fact the distance between f of y and f of x is less than what? It's less than anything I could possibly name. Might be if I wanted to, I could put epsilon here, and I could find a delta that works. Yeah, you're right. This should be delta sub x, right? But for now, if you don't mind, I'm going to put something here. It's a placeholder because I will see later what I need this to be. Okay, so I'll just put a little smiley face here. Okay, you name a smiley, and I can make this true for a particular delta x. That might depend on x. With me? Okay, we'll see in a second what that should be. I'm trying to motivate this argument for you. Okay, so the delta x balls cover, these cover x. So there is a finite subcover. Yes? So let me just, in fact, let me just draw some sample delta balls now. Here's one. And, here's another. And here's another. So let me finish. Let me suggest this. So there's a... Well, actually, I'm not even going to appeal to this yet. But here's a question for you. Would you agree I'd be done with my argument if I could show that for a small enough distance, if you give me 2 points that are close enough, anytime I throw them down randomly in this picture, boom, that they lie in one interval? Would you agree that that ought to be true? Why? Is it necessarily true? If it were true, here's the claim. So here's a question, and then I'll show you if we could answer this question, we'd be done. So can I find a delta such that if the distance between 2 points is less than delta, then P and Q are in the same cover, element of the cover, in a same cover element, cover set? If I could do that, then here's the thing that it would enable me to say. Because then what I could say is that the distance between P and Q, if you find me for any P and Q, like here's a P and a Q, would you agree they live in one of the they both live in one element of the cover, namely this one, yes? If you could do that, then I could bound the distance between P and Q by their distance to the center point of this cover. Right? What's the center point? This is in some cover set that's centered around X. Then the distance between P and Q is less than or equal to the distance between P and X plus the distance between Q and X, yes? And then what? Well, for that X, it had a delta X. For that X, if I were within if I were close enough, then their images would be less than smiley, right? So the distance between, what do I want? For then the distance between P and Q is bounded by the distance between Px and Qx. And the fact that these things, okay, so I just realized that I need to be a little careful here. Distance between P and Q is less than the distance from P to X and Q to X. Okay. And what does that mean? Yes, this is true no matter what, but I'm now trying to get a conclusion that relies on the fact that they're in the same. Well, no, I can do this because they're in the same cover set, so I can compare the distance. Oh, thank you. Actually, this is not Q, P and Q. This is F of P and F of Q. This is what I want to compare. Yes, I knew there was something that I'm... So this is F of P and F of Q. This is F of P, F of X, F of Q, and F of X. This is better. So now the distance between F of P and F of Q is bounded by these two things. Yes? And now these two things are going to be bounded as long as P and Q are within the same delta ball, then they are within the same delta sub x, right? So these things are both going to be bounded by Smiley over 2, or Smiley plus Smiley. If P and X, the distance between P and X is less than, since the distance between P and X is less than delta sub X, and the distance between Q and X is less than delta sub X, because they were in the same ball. And so what do I want if I want this to be less than epsilon? If I want this to be less than epsilon, then I need to make Smiley epsilon over 2. So that's the choice I should make here. This really should have been epsilon over 2. Okay? So what do I have? I have the requisite bound. If I could find a delta that's small enough so that any time two things are within delta, they live in the same element of one of these covers, then certainly they're within delta x of each other, because that's what this cover is, right? This cover is a delta x ball, right? Yeah, actually, I might have to be even a little more careful here, right? Because what if P and Q are on opposite sides of this this picture? Then they're within 2 delta x of each other, and I want them to be within delta x of each other. So, so I need to modify something here. Oh, yeah, that's right. You only care that they're close to x. Thank you. Awesome. Great. Good. Okay. Think too hard about things and then it becomes more confusing. Okay. Great. So here's the question then. Is this true? And the answer is yes. And this is actually a famous lemma in its own right, and it's such an important fact that it has its own name. It is what's called the Lebesgue covering lemma. That's an excuse to prove something that's not covered in your book, but is used very, very often in many contexts. So the Lebesgue covering lemma says the following. It says if you have, let's say, an open cover, U sub alpha is an open cover of a compact metric space X. Notice the compactness of the space X. Then, in fact, there exists a number delta bigger than 0, such that for all x in X, the ball around X of size delta is contained in some element of the cover. Is contained in some U sub alpha. That's the statement. And this delta has a special name. It's called the Lebesgue number of the cover. And this Lebesgue number will be, it will exist and be bigger than 0 if this space is compact. So here's the picture you should have in your head. We have some space. Let's call it X, and it's covered by a bunch of open sets, like so. And the Lebesgue number is basically a number, delta, such that you give me a little pancake of size delta, or radius delta. And if I throw that pancake anywhere in this picture, I claim it'll land completely within one of the sets. If there is such a number, it's called the Lebesgue number. And the claim is if the space is compact, this will be true. And can you see in this picture how small delta might have to be? Yeah, would you agree if I have a pancake of about this size, no matter where I put it, it'll lie completely within one element of the cover? Yeah? Now, this would not be necessarily true if the space were not compact, right? Imagine the following space. The open interval. Well, we can certainly cover the open interval like so. Let's just take a bunch of intervals that are basically narrower and narrower and narrower and narrower. And these are all open. Imagine these all be open sets. Throw a pancake down of any size and you're in trouble as you get closer and closer to the right. Okay? Well, it's not true if the space is not compact. Okay. And that's what we're saying here. If there's a pancake you can throw down so that it lands completely in one of those delta X balls, that's the delta that I'm interested in, then we're in good shape because we'll be able to complete the proof as desired. Okay? So let's see why this Lebesgue number exists. Okay, well, how might we start off this proof? Give me some ideas here. Space is compact. I have an open cover. Let's do something. Okay, yeah, how about take a finite subcover? Okay, well, how's that going to help me? Since X is compact, there exists a finite subcover. Let's call it U sub alpha sub I. And let's say I goes from 1 to n. Okay? So then what? Now I can remove all but finitely many of these balls. That's nice. Jenny?
Could you look at the intersection of these?
Okay. And what's your idea here? So you take an intersection of them and...
Well, just look at the intersection of every pair of them, and whenever it's non-zero, take, since that's open, find minimum ball that fits inside of everything.
A minimum ball, a ball of... Okay, so like as long as it's non-zero, as long as the intersection's not empty. Okay. And so why is that going to be a good pancake? It's actually it's a natural idea. You're sort of saying take something like this. And now which ball? Maybe this one?
Because that way it can't somehow be punched to the outside of both.
Okay. I'm a little worried about the same ball if I just move it over a little bit. Just a little worried. Although the intuition is a good one, but one has to be really careful because maybe it's not pairwise because you might have a really small... Should I look at all possible non-zero, non-empty? Okay, it's hard to do this, although I think if you're careful, you can create an argument like that. But I'm going to use a very similar idea here. So, how about the following? Would you agree that if these sets are open, then their complements are closed? Yes? So it makes sense if I have some point here to talk about the distance between x and, let's call this set, if this set is a particular set U sub alpha, then everything outside is U sub alpha complement. Yes? That's closed. Would you agree it makes sense to define a distance between x and the closed complement? Let's make a definition, and I'll convince you that this actually makes sense. Would you agree if a set K is closed, you can't stop me from defining a notion of distance between them? How about this? The distance between x and K is... How about the infimum of all distances x and y, where y is in what? K. Okay. Now, what can I say about this distance notion? What can I say about this distance notion? Well, I claim, this is where I'm going to let you do this part, the distance between x and k is a continuous function. This is using some of Laura's idea. Of x. Fix k, move x around. I claim this distance is going to be continuous. Okay. Oh, really? Okay, that's very easy. Use triangle inequality and change, x and compare distance between x and another distance, another point y. That's close. Okay. So this is, I'm going to leave you to show this. All right. Okay, so then what? Well, if these sets cover, then x is in at least one of the balls, yes? Or one of these covering sets, yes? And so the distance between x and its complement is going to be non-zero, yes? Now, if x is not in a ball, then in a covering set, this one, then the distance between x and the complement of this is what? 0. Okay? So we only have finitely many covering sets. Let's look at the distance between x and all the covering sets complements. What would it mean if I found? What would it mean if I found a delta, a Lebesgue number delta? What would that mean?
Then only this x is only delta close to one of the complements of the u alpha.
Yeah. Would you agree? The fact if I could throw pancakes down and have them land in a set, that's really saying that this distance from one of the complements is bigger than delta. Right? So if I could show that for at least one of the sets, there's a minimum delta ball around a point x that separates that minimum distance delta to a complement, I'm in good shape. Yes? So here's the slick idea. Let's look at all distances between x and its complement. And, okay, let's look at distance between x and u alpha sub I complement. There's one for every I. Now, I'm hoping to show that the minimum of all of these is bigger than 0, right? For every x. Well, look, you can't stop me from adding all these up and dividing by n. So this takes their average. I goes from 1 to n. This is a function of x. What can I say about this function, which is the average distances to the complements? It must be continuous because it's a sum of continuous functions, right? Oh, okay. What else? It's defined on a compact set. So it's a continuous function on a compact set. So, by a theorem we discussed last time, it must do what? Attain its maximum minimum. And actually, what am I concerned with, actually? Its minimum. Whatever its minimum value is. I have no idea what it is, but it attains its minimum value. Maybe its minimum value it happens to be, I don't know, let's call it delta. What would it mean for the average of a bunch of distances to be at least delta? It'd mean one of them is at least delta. And that's all I need. And that's the set that the pancake falls in. Okay? So it attains its minimum value, delta. So if f of x is always bigger than delta, then at least one of the distances ui complement, u alpha I complement, is bigger than or equal to delta. And so for this I, the ball of radius delta around x lives completely in u alpha I. That's what that distance thing means. Okay? Yes?
How does this show the delta is non-zero?
Ooh, excellent. That's the one thing we have not actually said. Why is delta bigger than 0? Jacob?
The smallest it can be is 0. There's at least one that's not 0 because it's in one of the sets.
Okay. So the fact that this thing is a cover means that what? For every x, what? It's in one of them. So this function has to be non-zero everywhere. Yes? Everywhere. So its minimum value has to be bigger than 0. Okay, so notice delta is bigger than 0 because f of x is strictly bigger than 0 at each x, since the u sub alpha I are a cover. Right? And notice we're really using the fact that it attains its minimum value, right? Because you might worry, yeah, maybe this function's bigger than 0, but its infimum is 0. Well, its infimum can't be 0 because this function achieves its minimum somewhere, and that minimum is always bigger than 0. Excellent question. Okay, very nice. What do we have? We have now established, in fact, our claim that a continuous function on a compact set achieves, it must be uniformly continuous. So this is true by the Lebesgue number. Well, by the Lebesgue covering lemma, but this delta that we're looking for is the Lebesgue number. Okay, let's take a couple-minute break. And after the break, I want to say something about continuous functions and connected sets. Yeah.
Keep taking x closer and closer to the edge over there. Doesn't that go to 0?
The distance between x and that complement will go to 0.
Yeah.
But the claim is the distance between that x and some other complement will probably start increasing as you get closer to the boundary.
But, okay.
So this function, which is defined everywhere and achieves its minimum, is clearly non-zero everywhere because every point has some distance, right?
Yeah, but but it's going to 0, and I can't make sense of that.
Yeah, so this is where we're really using compactness in an essential way, right?
Yeah.
This function is, you agree it's bigger than 0 everywhere.
Yeah.
Because it's an average of things.
I see that, but that part doesn't make sense to me now.
Yeah, well, if you get closer to this boundary, then I haven't drawn all the sets here of this space.
What if that was the whole set, though? Can it not be? It can't be because it's not closed. Okay, I see. Okay, that makes sense now.
Yeah.
Okay, that makes sense.
Yep.
Thank you.
Uh-huh. Okay, let's resume. So we've seen that continuity preserves lots of different things, right? Continuity preserves limits. Continuity preserves compactness. So the image of a compact set is compact. And as somebody conjectured last time, continuity also preserves connected sets. So if you take the image of a connected set, then in fact, the image is connected. So suppose f from x to y is continuous, and E is, let's say, a connected subset of x, then f of E is connected. Very believable result, right? You can't continuously deform a set X into something that's not a connected set into something that's not connected without introducing a discontinuity, right? How are we going to prove this? Time for a picture. Here's a space X. Here's a space Y. Okay. And here is a function from x to y. Okay. Smiley face. Sorry, that was my only excuse for drawing it down there. I'll just draw it here. It's fine. Okay. Let's see. Oh, I have a connected space here. Yes. How's this? Here's a subset E, which is clearly connected. Maybe it's the state of California. Okay. Yeah, it's currently, California's connected, currently, but may not always be. Okay. Okay, great. So the claim is the image is connected. So what's the perfect way to start off this proof? Because connectedness, what does it mean to be connected? It's a set cannot be separated. Not the union of two non-empty separated sets. So it's always easier actually to work with sets that aren't connected, right? So if I want to show the image is connected, maybe I should do this by contradiction. Suppose f of E is not connected. Well, what does that mean? That means f of E is what? Separated. It's the union of two separated sets. And I'm just going to say that by saying a separation. And of course, we know what a separation means. It means they're non-empty, right? And A closure intersect B, and A intersect B closure is what? It's also empty. Okay, remember that. That's what we're going to need, that fact. So let me just draw a picture that can't be true. Suppose I have a set A. This image looks like this. F is continuous, which means all sorts of different things.
But we can find a ball around some point in B that does not contain a point in A, but it needs to because things need to be mapped close enough to each other.
Okay, so you're thinking in terms of metric condition. Let me encourage you to think in terms of the topological condition, because this really is a topological fact, right? It's not. It really doesn't depend on anything related to the metric. So maybe the topological argument would be easier. So let's see. Would you agree that if A and B were both open sets, this would be very easy to show, yes? If A is open, then, because F is continuous, the preimage is open, and B, preimage is also open. This is a union of two open sets, and in E, these sets are clopen. Okay, because no point in here can be a limit point of a point in here because they're interior to the other set, right? So you'd be in good shape if they were both open. So we're going to do something that's very close to this idea. So let's call this set A and this set B, and consider the claim. So notice, I'm going to give this set a name. I'm going to look at whatever A is. I'm going to look at its closure. That's one thing I can do. I'll close it. A closure. And I'll look at B closure. Is that okay? Now, what do I know about A closure and B closure? They what? They're closed. Thank you. But because of separation, what's true about the closures? A closure does not intersect what? B. It might intersect B closure. So let me just suggestively draw the closures so that they intersect. Okay? Okay. What's the next thing you might do? Since I don't know anything about A and B, they're not necessarily open or closed. If they were open, I could take their inverse images and these be open. If they're closed, I could take the inverse image. So let's take the inverse image of A closure. What do I know about that? It's closed. Good. So notice, let's call this set KA, which is the inverse image of A closure, and KB, which is the inverse image of B closure. Let's notice that these are closed, since F is continuous. Okay. Great. So they're sitting over here somewhere, yes? And maybe they look like this. Okay, that's KA and KB. Right, Northern and Southern California. Okay. Right. Well, what can I say here? What I want to do is use these sets somehow to produce a separation of E, which would give me a contradiction. Yeah? So what's the separation of E that I might suggest? Well, give me a proposed separation of E. Well, Ka and Kb is not quite going to be a separation because they might intersect. And so their inverse images might intersect. Yes? If I take the interiors, I might be in trouble because I might leave out some points right at the boundary. How about just the inverse images of A and B? So those are smaller sets. So let me write that here. Let's call a set E1 and E2. Let's let E1 be the inverse image of A. And, of course, that might include lots of points, so I'm just going to intersect it with the original set E. And let's let E2 be the inverse image of the set B intersect E. Certainly, these are clearly disjoint, yes? Because A and B are disjoint. So inverse images are disjoint. Are they non-empty? Yes, why? Well, A and B are non-empty. And this is the image of E. So these have to be images of points over here and here. Okay, what's the last thing I want to show? Well, I hope to show there a separation. That is, the closure of this one doesn't intersect this, yes? Okay, so I claim they're a separation. Let's see why. Well, notice that E1, I claim there's something very interesting. So the picture should be analogous here. Yes, E1 is contained in Ka, which is closed. Okay, notice E1 is in Ka, which is closed. Let's see, why is it contained in? Oh, it's the inverse image of something smaller, right? In E. Okay, good. And in fact, E2 is contained in Kb, which is also closed, right? So can you justify for me why E1 closure contains no point of E2? Well, Ka is closed, right? So E1, this is contains, Ka contains E1, Ka is closed, and it's therefore the smallest closed set. The smallest closed set containing E1 is E1 closure. This is a closed set containing E1. So E1 closure is in Ka. And E2 closure is contained in Kb, yes? Okay, we're almost there. Why is E1 closure not intersect E2? Well, it's E1 closure is in Ka. Ka, I claim, does not intersect E2. And Ka does not intersect E2. Why? I claim this is empty. Why? Look, this is equal to the inverse image of what? A closure. But A closure is disjoint from B. And this thing is contained in the inverse image of B. And A intersect B is empty. This is why. Okay, that's not formal math writing. This is giving intuition. Okay, so I've used the separation property here, and similarly you can show the other thing. And similarly, Kb intersect E1 is empty. And therefore you have a separation. So E is separated. Contradiction. Okay. Okay, that was basically technical, but it's following your nose. The idea is in this picture. Okay, so the image of connected sets is connected. No big surprise there, but it gives a very, very useful consequence, which you learn, I don't know, maybe in middle school or something. It's a theorem known as the intermediate value theorem. Can you see why that's a theorem about images of connected sets? What does the intermediate value theorem say? It says if you're dealing with a function on the interval going into R that's continuous, and let's suppose the image of the endpoints, there's a point in between the image of the endpoints, C lives between FA and FB, then I claim there exists an X in AB, in open AB, in fact, such that f of x equals c. That's the intermediate value theorem. And everybody's favorite picture of the intermediate value theorem is something like this. A, B, well, I'll draw it this way. A, B, and continuous function. The claim is between f of A and f of B, you give me a point C, and I claim there is a point X that achieves the value C. Okay. Hopefully you can see why this is a consequence of the theorem about connected sets. Why? So let's see. Maggie's looking at this and saying, oh, look, I have a connected interval, AB. Its image is connected. Suppose the image never hits C, but it hits f of A and f of B. Then the image would be disconnected. In fact, you could disconnect it using the part below C and the part above C. I claim that's a disconnection because the closure of a part above C can at most contain C. It can't intersect the other part, and vice versa. So the proof is noticing that FAB is connected implies the image is connected. If C is, but if C is not achieved, then C would disconnect f of AB. Then C would disconnect it. Okay, I'm saying this very informally. Formally, I would say take the interval from C to infinity and intersect it with f of AB, and take the part below and intersect it with f of AB, and that forms a disconnection. C would disconnect f of AB. That's the basic idea. Okay. Look at this part and look at this part. All right. Okay. So one comment here, is the converse true? If a function has an intermediate value property, must it be continuous? If it's always the case that the conclusion holds, how many people say yes? How many people say no? Okay, yeah. And you're probably wondering, you're probably thinking, well, I didn't state it as an if and only if, so it's probably not true. Converse is false, and I'll just show you an example. Here f of x equals, let's let it be 0 at x equals 0, and let's let it be sine of 1 over x at, for x not 0. This has a special name. It's called the topologist sine curve. It's the source of a lot of headaches in analysis, or actually a source of a lot of interest, right? If you want to test things out, this is a good one. Here we go. So take the sine of 1 over x. It basically oscillates between 1 and minus 1, but it oscillates more and more as you get towards the origin. Right? Similarly, this does the same thing on this side. And then at 0, you just tell it to be 0, right there. Claim is this function is not continuous at 0. But it satisfies an intermediate value property. Okay. So one of the things I want to talk about next time is actually, since we've said a lot about continuity, I want to start talking about discontinuities, right? So what does it mean to be not continuous? I mean, so here's an example. Is it possible for a function, we know what it means for a function to be continuous everywhere. Is it possible for a function to be discontinuous everywhere? There's a question. Is it possible for a function to be discontinuous everywhere? How many people say yes? How many people say no? Yeah, okay. Well, we're going to explore this question next time, so I'll let you I'll let you ponder that. Stick around if you have questions about the homework.